Hi everyone. It has been a while since I made my last FPAA learning tutorial. So I was thinking right now it might be a good opportunity for me to share how people can use FPAA to realize or implement nonlinear system. As during my PhD study, I have been using FPAA implementing a lot of nonlinear system. So the very first one, when I started, is I was able to use FPAA to realize Lorentz system, which is a chaotic attractor. During the time when I studied FPAA by myself, it's also a very time-consuming process. It took me almost the entire summer, a couple of months, to eventually understand how I can correctly implement everything from FPAA, especially on nonlinear system. Other than Lorentz system, since it's actually a very simple higher order nonlinear system, and other than this, we also have this Duffing equation or Duffing oscillator, which is a very typical nonlinear oscillator. And in real life, there is a lot of models that can be modeled by, or a lot of physical stuff that can be modeled by Duffing equation and Duffing oscillator. And one of them can be a pendulum system. And Duffing oscillator itself can also represent a chaotic behavior. Other than that, during my PhD study, I've also implemented multiple ones. So, such as one of them, as I just mentioned, I was using a pendulum-based adaptive oscillator, which also shows you chaotic behavior. But other than the chaotic behavior region, it works as a very nice analog signal analyzer. So this oscillator can learn the phase information and frequency information of the unknown input. So this is one of the paper that I published. I also have FPAA implementation. The other one is a pure adaptive oscillator demonstration that was also implemented through FPAA. So adaptive oscillator, so here is also one type of nonlinear oscillator. But the benefits of using this oscillator, a single one, you can actually use it to learn a unknown signal input, let's say amplitude, and also frequency. While the input information can be very complex, let's say the input can be composed of multiple frequency components. If you only have a single oscillator over there, you might only be able to learn one unknown input information. And also depends on your initial condition, which frequency component can be reconstructed by a single adaptive oscillator is also very important. Well, if you have, let's say, maybe multiple multiple frequency components and also multiple adaptive oscillator as an array, so it can work as a frequency spectrum analyzer and reconstruct the whole frequency spectrum of an unknown signal, or in other words, can also reconstruct the unknown signal waveform. So maybe you can also check out my paper. So to take a look how I use FPAA to implement this nonlinear system or nonlinear oscillator. So I was using the Anodyne FPAA and using the Anodyne FPAA simulator. So it's very useful. So I would say FPAA is really a fast prototyping tool which you can utilize to quickly demonstrate your experimental results. Especially from mass equation map into the analog circuit system. So I have been before using, let's say, LT-Spice and building everything from LT-Spice. So you have to go to breadboard first, and if the breadboard works fine, then you have to build your own PCB, right? So that's a really long process. So using FPAA, I would say we can reduce 80% of the prototyping time. So from this video, I would like at least to collect some information or input from the people who are interested. If you are really interested, I would like to start making videos to show you how you can how you can implementing nonlinear system from FPAA. So if you really like it, and please let me know how you think about it. Then in the future, I might need to make another few videos to teach you how you can achieve nonlinear system or nonlinear oscillator through FPAA. So I might start working from a simple case where we can achieve Lorentz system in FPAA. Okay, thank you everyone for watching.